Hello all of you redstone lovers, this is me so lost on Stym's redstone server, giving you another tutorial video. This time we are doing Minecraft PCs, a basic introduction to the components, how they're used, what they're used for, how they're integrated together into each other, and ROM. I've had all sorts of people asking me all sorts of questions, so I'm doing this tutorial video in order to answer these questions. After you have completed watching at least the beginning portion of this video, which I will tell you when the beginning is over, before I get into the slightly more advanced stuff, then you can come back to the server and ask me your questions. Please wait until I'm finished with the ROM explanation before you actually come in and ask me anything. Alright, because chances are it'll be explained. So, for the tutorial, I'm going to use my wireless PC. And thanks to Wosh0007 for his wireless plugin, which he coded completely by himself from scratch using nothing but command helper. Alright, so the buses are missing. That's because everything is done wireless, so obviously yours is going to look more like that one up there. Alright, since it actually has all of the bus work into it. Now, the first thing I want to mention is I use a CISC style build instead of a RISC style build, and the only thing you really need to know about the difference between them is that a RISC style build has one integral ALU. It doesn't have separate components for everything, whereas a CISC system actually has multiple separate components, like a separate adder and a separate multiplier, etc. Alright? Now, this system is currently set up to do multiplication, and after we do the ROM explanation, well, as part of the ROM explanation, rather, we will explain to you the multiplication system and how the ROM is programmed. So, first, keep in mind that this is a CISC system. This is an ICA adder. The green and the blue is A and B reversed. And these are the inverters for invert A and invert B. Well, B lower, A upper. And our output. So this is our ICA adder. And then down here we have a logic core. Or at least what I call a logic core. Now, what this guy is this is simply an XOR gate. The first XOR gate that you get off of a ripple carry style adder. Alright? And how we have this set up is that I can use the XOR output, or I can use, via this torch here, the AND gate output. Alright? Or I can use this line up here and disable this AND gate, turning the XOR into an OR gate. So, having that, now we have OR, XOR, and AND. We place an inverter on the output of the logic system, and now we have XNOR, XOR, and exclusive AND. Or NAND, rather. Or it's XNOR, NOR, and NAND. My apologies. Alright. So, however you do your ALU, whether it's an integral ALU or a CISC style with a separate adder logic core, that's up to you. Now, for selection of these, we'll get to that later when we actually get into the ROM. For now, just go ahead and picture this as one entire unit. The other component that we need for a computer is the RAM, which is this guy here. Alright? Now, to pause here a brief moment, most people put registers on the inputs of their ALU, and this is because most people use a single read RAM, as in RAM that can only read from one location at a time onto a single bus. Me personally, I don't use any substandard Redstone components. If it's not running on the purest of Redstone at the highest of tech, I don't use it. Which is why you see green and blue on the back end of this, because this is a dual read RAM system, meaning I can read from two different RAM spots at the same time onto two different buses. In addition to being dual read RAM, I always make sure that all of my RAM is write-back capable. Now what this means is that I can read from RAM slot 1 and RAM slot 2, run those through the ALU, and save my answer back into RAM slot 1 or 2, as in I can write back to the same location I am reading from. That's what I mean by write back. Okay, so we don't have any registers because I've got dual read RAM. Well, I do have a register, but we'll get to it in a moment. We don't have any input registers, okay, because of the dual read RAM. So we've got the inputs of the ALU hooked up to the outputs of the RAM, and we have the input of the RAM hooked up to the output of the ALU. Fairly straightforward and simple. Pretty much set up just like one of those two guys you see there in front of me, either this one or that one. Output of RAM, straight into the adder, right back up into the right bus. You can go ahead and stick yours together like that if you wish. It makes a very fast setup system. The only other thing that we'd want to do is to, on the back end of the RAM, is where you'd probably hook in your UI inputs or some other thing. And, you know, whatever else you need to, you find a way to hook the stuff up, alright? Just keep in mind that when you actually do your computer, put your components in a logical fashion. Don't just, you know, stick one component here and paste this one over there and then do a whole bunch of funky jalopy bus work in order to make it work together. Nah. Plan your computer. Put all of your parts in place, fiddle with the alignment, fiddle with the spacing, alright, until you can see in your mind's eye a nice logical layout to the busing system. And we'll just use this computer as an example. This is just another 8-bit computer based off of the wireless one, but this one is wired. I have the RAM inputs and then the RAM outputs over on that end. And if you notice, I use this crossover busing method. What this actually does is ensures that every line is of equal length. Now, with the spacing that I have here, the lines don't exactly come out even because I'm doing, 4 wide over there and 3 wide over here, or 4 and 4, and these guys are 2 wide. But with the way that the repeaters are set into here, you can see a repeater there, and it all comes out actually timed correctly. Keep this kind of stuff in mind when you're laying out your computer components. The next component that you're going to want to have for your computer will be a shift register, which is this brown guy here. You'll notice all of these extra bits sticking off of this shift register. We'll get into those guys later. That is part of the conditional jump system. Remember, do not come and ask me questions until it is complete, alright? I will tell you when you can come ask me questions. Now, the shift register, technically, we only need to have shift down. And why this is because in a base 2 system, if you're going to shift up, you can basically multiply the number times 2. And we can do this with nothing but the ALU. And the easiest way to multiply a number by 2 is to do A plus A equals 2A. So, if we want to shift A up 1, we read, like say our A is in memory slot 1. Okay, we read memory 1 onto the A bus and to the B bus. Okay, and now we have an output of A shifted up 1, which we can save wherever we wish. So, if you use that particular strategy, we can then take all of the repeaters off of the shift down side and use the shift down piston arrangement as reset register. Now I actually do the reset register in a different fashion on here by, we've got the shift up and the shift down. You see this one is shift down, but we also have a shift up receiver here, so that if we shift up and down simultaneously, we get no signal out of this monostable. And over here, we have shift up and down on an AND gate, so if we shift up and down simultaneously, we actually shift down through the entire cycle, and from the length of the clock, we actually have enough time to shift everything right off the end of the register and just completely zero it out. Now the way that I have my shift register set up is it only reads from the B bus and it only writes to the B bus. Now just to preemptively explain a little bit of this, okay, for the jump condition, we have the most significant bit. What is it? Yeah, the most significant bit. So we have a tester on the highest bit of the register. We've got the least significant bit check, and then we also have a has number check. If you see the way that these repeaters are pointed, it'll power this block, powering the redstone below it. So if any space in the register whatsoever has a number in it, we'll get a signal out here saying that yes, register has number. We'll do a bit of explaining on the jump stuff here in a bit. This orange thing is a lovely little double dabble provided by Black Belt Jr., and it's not currently installed yet. I had the old style one, which was like 7 ticks per step, and this guy is 3 ticks per step. A lot more efficient, a lot faster. I still, however, do have this row down here to where we can read a binary style output. So, we've covered that we need RAM. We've covered the method in which the RAM is wired to the ALU, and we have a single shift register on the B bus that we can either choose to use or not to use. See, we have a separate write to, and then we have a separate read from. Alright, so now that we have the RAM hooked up to the ALU with a shift register stuck in the middle of a bus, we're starting to get the basics of a computer. Alright, so most of you people have a whole UI setup like this that's got 50,000 switches on it to control the CN and invert A and invert B and everything else about your system, what RAM slot to read from. You've hooked everything up to the UI. Now, this is good for diagnostic reasons, but you're probably going to run into an issue that all of that busing that you just did is going to prevent you from busing everything else that we need. You might think of, what else do we need to bus? Well, that's what the ROM, where the ROM comes in. Alright? So, conditional jumping will come after the ROM explanation. Now, we are actually going to explain what the ROM does and why we need it. Alright? Ignore these gray parts. Those are part of the jump system. The yellow is the ALU control, the red is RAM write, blue is A read, green is B read, and then we have a couple of other things here. We've got the use the UI 2, use UI 1, we have our invert jump signal, we have a jump condition selector, we've got a register control, clear RAM, write to the double data, and this last line here is stop. If you do not understand what stop means to a computer, please do not build a Minecraft computer. If stop is too much, just too big of a function to comprehend, you're not going to get anything else. Please close the window and go about your usual Minecraft routine. If you do understand what stop will do to a computer, please continue. Now, I use what is called a muxed or mixed compartmentalized instruction set. Compartmentalized because I use a CISC system, and some components we will not use as we are using other components, so they can actually be muxed together. As in this computer up here, you see those teal lines. We'll just come up here a moment and explain what the heck I mean by a compartmentalized muxed instruction set. These 4 lines are responsible for all of the jump control and register control simultaneously. But we can only use one at a time, as we're about to see. By default, you'll see that all of the outputs going to the clock system, all of our jump controls are shut off, and these 3 lines are allowed to pass through into this upper region here. Now, this upper region is, wait. This bit here, alright, is our basically mux control of where the other 3 signals are going to go. Now, if we leave it on default and we're controlling the shift register, this line here is also a mux control, specifically to mux control the register. Okay, with this line being off, we are given, in between these 2 blocks, we are given the signals to these 2 outside rails and not these 2 inside rails. Now, these outside rails, if we go up and take a peek at the actual shift register, the outside rails control the read from register and the write to register. And again, with this register, it is only hooked to the B bus. Alright, now if we turn that second line, we'll just go ahead and say this is a binary 1, 2, 4, and 8. So the 4-bit will control the mux of whether we read or write or shift up and shift down. So we turn that bit on, and now we're doing shift up and shift down. We don't have a block the way we do on the other one to stop these shift up and shift down, but we do have a monostable, so it will only shift a little bit. And again, with this AND gate, if we shift up and down at the same time, we overpower one of the shift rails and end up shifting all data completely off the end of the register, erasing all content within the register. Okay? And this is what I mean by muxed. Okay? As in, these lines will do multiple things depending on how the other lines are set. Now, compartmentalized, okay, means that certain things do certain things. Like this blue section here does the jump control and the register control. We'll get into jump later, like I said, just wait, okay? And the yellow does all of our ALU control, which actually does both logic and adder control. I said fall. There we go. So to show you, to show you how I do this, alright, again, we're going to look at this as if it's a binary code. Bit 1, 2, 4, 8. Okay? So, by default, the 1 line over here is the mux of, are we going to use the adder or are we going to use the logic core? By default, we are set to use the adder. If we actually set this by programming it That means now on this line we're actually going to use the logic core. But in multiplication we don't need any of the logic core. The only thing that we need is simple adder function. Okay? So you can see on here that for the logic, or for the adder, the 2 will turn Cin on, the 4 will turn invert A on, and the 8 will turn invert B on. So in order to do subtraction, I would say, alright, this has got to be 0 to use the adder. I need to do Cin and not B, and this will subtract A from B. And that's how we tell the ALU that we're going to subtract on this particular line of instruction. Very easy, isn't it? You just simply say, on this line, set up the adder as such so that we can do whatever we want for the rest of the stuff, which we'll get to in just a brief moment. Now you'll notice on here, if you actually do a decode of the logic functions, you'll notice that the 2-bit signifies use the AND gate, the 4-bit signifies use the OR gate, and the 8-bit is our NOT result, or invert the out, so that we can get a NOR, XNOR, and NAND. Now, for the RAM, there should be a 4 there too, because the heck? Sorry, I should have noticed this last night when I actually sat here and talked to myself for an hour, because this is the second time that I've recorded this, because the first time, for some reason, Camtasia decided to use the digital input instead of the actual microphone input. Ugh. Anyway. Alright, so, just like any binary number, if I want to use RAM slot 5, I turn on 4 and 1, which totals 5, and that tells the system to use RAM slot 5. Most of you people just do this as RAM slot 1 read, RAM slot 2 read, RAM slot 3 read, RAM slot 4 read, RAM slot 5 read, RAM slot 6 read, and you're going to end up with a massive ROM because you have to accommodate all of this extra stuff. If you notice here, this little bit here is actually a binary to signal strength adapter that I built. So we put in our binary in here. Normally you would just use your little binary decoder, and then the binary decoder does the urinary, or one item at a time, selection of which actual RAM slot that we're going to use. Alright? So, now that you know how to use those decoders on your RAM in order to shrink your ROM, you can actually use 2 bits, and you can actually use 4 RAM slots off of 2 bits. Personally, I don't use 0, so whereas I might be able to address 8 on here using 0, I only have 7, because I use 0 as null, so that it just ignores using anything of that at the time. And on the other computer, I have 2 7-byte RAM cores, so technically address 1000 or address 8 is unused, but I've actually set it up so that if you call bus 8 for a read, you actually read that particular user input. And writing to number 8 actually does clear RAM. So I was able to remove a couple of functions, and by adding 3 lines, I was able to double the RAM and compress several functions back down into a muxed instruction set. Alright, so we've addressed basics of ROM, We've addressed the basics of an instruction set, the basics of how to control your ALU to do what you want. We've got these two guys here, which tells this computer to use UI on bus B, or UI2 on bus B, use UI1 on bus A. This is our invert jump signal. This is our jump condition source selection. And I have 4 locations to which we can actually get a jump signal. The 3 I had previously explained on the shift register, and the 4th being the carry out or overflow on the adder. Alright, here's our shift register control, and that's a note for later. This is our clear RAM function and everything else. So now is the time that you can actually come and talk to me and ask me some questions. Alright? Now, before you do that, the next part of this video is going to be jumping / conditional jumping, its uses and why we need it, a rundown of my multiplication program, which includes more information on conditional jumping and how to program the ROM. So go ahead and pause, go ask me some questions, or highly recommended you finish watching the video. Now, for conditional jumping, yeah, you've got the system clock that you need. I totally forgot about this a moment. We got the system clock, alright, which actually gives us our clock pulses in order to step the counter. Okay, this guy right here is a counter. I do everything in ultra compact signal strength where applicable. This is our signal strength decoder, which you would probably use a binary counter and a binary decoder, much the way that the next computer system I'm going to be putting together uses a binary style counter. This part here is for our jump control, and you'll notice this little weird guy here for blocking the signal to the ROM line selector. Now, this is something that you're going to need so that as you're running your code from your computer, when you go to select the next line of ROM, you will temporarily have 2 lines of ROM open at the same time. Okay, as in you're going to be running 2 lines of instructions simultaneously. This is very, very bad. Alright, so we actually stop the signal going to the ROM to allow the counter to do its count, allow the decoder to get a fresh signal all at once so that we do not get any erroneous line selection. Alright, this just makes sure that we only have 1 line of ROM selected at a time. Okay, this guy right here, and this guy right here, and this guy right here is part of our jump system. Alright, now normal operation as we are going through, our clock goes and we get a master write signal. Now the reason why I do this kind of a setup with a master write signal, which you'll actually notice on this computer up there, is that white line that you see, the InstaWire line, so that I can get an instantaneous write to all parts of that large-scale computer simultaneously. What this does, this is our end of cycle thing. This actually allows the signal to go into the RAM to write. It allows the signal to go into the register to write, and it also allows the signal to go into the double dabble to write, and it also allows the signal to come into the actual jump system, which actually, instead of doing a centralized invert jump and all of that, I actually have it per thing because, heck, I mean, it's wireless. I don't really have to wire this stuff everywhere. So the way that this works is that the write holds this on at all times. Once we've selected this area as our jump source selection. That goes like that in order to allow the signal to come through, and when we actually receive the right signal, blink, our signal will actually get through and we'll be allowed to jump. Okay, now what our jump system actually does is instantaneously upon jump via this monostable, so it's a tiny bit delayed, but not as delayed as our actual clock tick. Okay, our clock tick actually happens in the middle of this reset happening. So the reset, this block is lifted up, the counter is reset to 0, we get a clock pulse, which the counter can't clock because there's no signal coming into the back of this comparator for the counter to actually work. This block drops back down, counter is ready, the counter is ready to be programmed, alright, and then after this extra bit of delay, this block comes down, allowing our programmed jump address, which comes from this point here on the ROM, okay, to actually tell us where it is that we're going to be jumping to, comes into the decoder, is decoded into a signal strength, like say we're jumping to line 7, so 7 signal strength comes out. We then force program the counter to have that number, and how you do this on a binary style counter system is you would have to have a way to TFF, toggle flip-flop, each individual piston on its own. And then when you do the reset, you actually do a counter reset and then forcibly program the line that you want to go to. Alright? That's just the basics of the jump system. Okay, this will allow us to, at random, decide that we need to go to a different line in the program. Combined with this jump condition, in order to trigger the jump system, we can actually have conditional jumping, as in we don't just specify always jump to line 4 on this line, or this guy's line 5. Don't always jump to line 5, but if this condition is met, then jump to line 5. Okay, now we're going to get into the ROM programming and conditional jumps. This, you can actually throw off these last 2 lines, okay, because that's just display the answer and that's stop. So, within 1, 2, 3, 4, 5, 6 lines, I can do any bit length multiplication whatsoever. I can take the same ROM, I can upgrade all of my components over here to be 16-bit, or 32-bit, or 128-bit, or 1024-bit, so long as the bit length of the adder, the register, and the RAM are all equal. What this program does is I had the page open, the shift and add method of multiplication. I have this listed out here in both English and in machine code. So on the first line, we are setting up the computer on a fresh run. So we clear the RAM, we clear the register, which actually happens first in the cycle, the RAM clear. The register clear takes the entire cycle, so because we know the register clear takes the entire cycle, we know we cannot write to the register on this line of code. But we can still write to the RAM because RAM clear happens at beginning of cycle and RAM write happens at end of cycle. So we read UI A and write that to memory 1 and clear the RAM and register. So we write to RAM slot 1, we read UI1 onto bus A, and we shift up and down simultaneously to clear the shift register, and we do a RAM clear. Pretty simple and straightforward. The next line is the read UIB and write it to the shift register. And that is simply UIB read and write to the shift register. That's it. Just 2 torches for that entire line of ROM. Now, the meat and potatoes of the program, the 4 lines that actually loop and do the stuff. Alright, on this line, we do if the least significant bit of the register is 0, then jump to line 5, meaning that we don't actually do our accumulation for the multiplication on this step. Okay? So, line 3, pardon me, is invert the jump because we expect to have a 1 if it's good. So if we have a 0, this invert jump will actually give us a true signal out, or an actual, it'll give us a redstone signal rather than not giving us a redstone signal. So our jump condition select is we tell it to use, let's see, bit 1, bit 2, 210 is use register low. So this selects that our jump signal is coming from the least significant bit on the register. This inverts our jump signal, and all the way down here in our address we have an address of 5. So that we'll skip line 4 and go to line 5 if there is nothing in the least significant bit on the register. Now let's just for a moment imagine that there's a bit on the least significant bit, which means that if register equals 0 comes out as false. So we do not end up jumping on this line. We just continue on to the next line as if that line just didn't even exist. Okay? Now on this one, we're using the memory 2 slot as our accumulator. And if you're wondering what accumulator is, you've got $10 in your wallet. You find $10 on the ground, and you put it in your wallet. You find another $10 on the ground, and you put it in your wallet. You find another $10 on the ground, and you put it in your wallet. You have just accumulated $40 in your wallet. Simple as that. Just totals everything up that we tell it to. Okay? So we do memory 1, which is our A or shifted A, plus memory 2, which will be our final result at this point at 0, or whatever it happens to be in whatever part of the cycle that we're in. Alright, so that's our accumulation step. And we simply do line 4, read from memory 1, read from memory 2, and write back to memory 2. Easy as pie. Now the next line does all of our shifting for us. Memory 1 plus memory 1, write back into memory 1, shifts A up. We tell the shift register to shift B down. Alright, and this is done by A read 1, B read 1, memory write 1. So on all those lines it's just 1, 1, 1, 1, 1. And then our shift register has a torch for shift down. Okay? Now this line here says if there's still data in the register, jump back to line 3. So we do a jump condition check on the register has number or register empty. Okay, empty. Empty. You would not believe how many stupid truckers cannot possibly comprehend that empty means empty, because they don't feel like scribbling out E-M-P-T-Y when I'm trying to run through cataloging 500 friggin' trailers in an hour. Okay, I just scribble empty, and I can tell them, go find a trailer with empty on it. And then the idiots come back and says, oh, I can't take that trailer, it's marked empty. Ugh. For real? You can't take an empty trailer because it's empty. You asked for... Anyway. Okay, so if the register is not empty, okay, meaning that we actually have a signal coming off of our register has number line, that will tell us to jump back to this line here. Okay, now we've already done shifted, so if we were done, we've shifted everything off into oblivion and our register is empty, this line will fail, and we'll just go on to display the answer and stop the system, just for this test program. Now, if it actually does have data, we go all the way back here to line 3, because we shifted back here on line 5. Now, we're set up to do the next bit. So, if the least significant bit in the register equals 0, skip the accumulation step, and if you actually look at the multiplication via shift and add method, you'll understand this better. Alright? So, we skip this step and just go straight to shifting A and shifting the register down in order to prep for the next step to see if the least significant bit of B is a 1. Easy as pie. So, this thing, if we actually input all 8 bits into the system, this system will loop through 8 times until it's shifted all 8 bits off the bottom of the register, and this line finally fails, and it goes into displaying the result. Now, our result can only be 8 bits long, so if we multiply solid 1s across the board by solid 1s across the board, then we're going to get a massive overflow of data, and we will not have the proper answer displayed. Okay? Keep this in mind when you're trying to do your system. You have to manually control your inputs. I just know several patterns that I can stick into here that will actually give me a 255 output just from, just from the patterns alone. Alright? It's some weird stuff. Like, let's see, this and this times, that'll yield 255, or, hey, I said flip you, or that'll yield 255, you just gotta pay attention to your data set and know the limitations of your system. And speak of the devil, there's Gort. Alright, so the ROM is just stupid easy. I mean, look, it's just wires that crisscross back and forth. You've got the top lines that are selected by your counter, your program counter, alright? Yes, that's what selects what line of the ROM we're going to use. The opposite way, the lower lines actually connect to all of the stuff that your switches on your UI connect to, which is why I said that you probably won't want to wire all of that stuff up or dewire all of your debug stuff, or wire in your debug stuff last, so that the normal run operation of the computer takes priority and debug is an afterthought. Alright? Just trust me, having debug as an afterthought and having to make your debug wires go all sorts of crisscross crazy is going to be a lot better than trying to get your actual control lines to go in crisscross and spirals and put all sorts of delay in it to make the computer's actual automatic runtime go slower. Alright, so now that you've had your brief introduction to Minecraft computers, some of the simple basic components that go into it, how they hook together, the basics of ROM, simple ROM programming, and how the ROM attaches to the system, now you can go ahead and come back onto the server and ask me your questions. But please don't ask me anything that I covered here in the video unless you need some specific clarification on something. I tried to do my best to cover everything that I could in as short of a time as I could. I do believe that this guy is shorter than it was last night by a whole 25 minutes. So, thank you for listening. Again, this is MeSoLost, moderator on Stym's Redstone server. And just so that you guys can see where it is that you've got to go to, beta.redstone-server.info, default port. Please feel free to visit us and have some fun. Thank you, and goodbye.